We're going to carry on our merry way with some more gas laws. We talked about already how Boyle's law was one where they were inversely related because as pressure increased, volume would decrease and vice versa in order to remain constant. And we talked about that in the last lecture. Today we're going to talk about Charles's law. Charles doesn't have a wig, obviously, like Boyle did, but Charles's law is going to deal with temperature and its relationship with volume. So we'll see that here with this relationship. Here we have volume over temperature. So they are directly related. It's not an indirect or inverse relationship. It's a direct relationship because as volume increases, so must the temperature in order to keep the constant the same, or as temperature increases, the volume increases. And this should make a lot of sense. I'll show you some pictures here in just a minute that I think will help make that point. One of the things I want to bring out here is that we make sure that our temperature is always converted to Kelvin before you do this. This will not work without that, so make sure that you do that. This should make a little bit of sense, though. As one goes up, we have a direct relationship. As one goes up, so does the other. We know that gases bounce around and bounce off of each other, and if we increase the kinetic energy due to an increase in temperature, it's going to increase the volume. And you'll notice we have that relationship here. So let's go back a slide. It says the volume and absolute temperature of a gas are directly related at constant mass and pressure. So we're keeping the amount of gas and the pressure constant in this example. So this is similar to some things you've already had previous experience with. So here we have a balloon and it has a pressure pushing down on it from the atmosphere, and it has a certain volume that it takes up at a particular temperature. We're going to leave the pressure the same in this case. The air pressure hasn't changed, but we cool it, so we reduce the temperature, which reduces the kinetic energy between the molecules and is going to reduce the volume, because we know that Charles's law says if we reduce the temperature, the volume also decreases given the same number of molecules and the air pressure being the same. And you experience this too in the wintertime when you have a soda bottle that is mostly air and you leave it when you go in the house at night and the temperature drops drastically and the pressure is about the same on the outside of the bottle, but you'll go out and the bottle will be caved in. And the reason it's caved in is because the temperature has slowed the molecules down, which is going to decrease the volume. And so it caves in because the air pressure is the same and the volume reduced. And this is a Charles Law demo, but it has to do with a train car instead. Same principles at work at this as well. So let's look at how to do a problem, one of the math problems that accompanies this Charles's law situation. So we have a gas that occupies 473 cubic centimeters. So here's our volume at 36 degrees Celsius. Find its volume at 94 degrees Celsius. First thing you have to do is make sure that you realize you're dealing with Celsius and not Kelvin, and you have to change it to Kelvin. Now it doesn't matter if we leave the volume in cubic centimeters, that's not a problem. We'll just make sure that our answer is given in cubic centimeters as well. So as the temperature goes up, we expect the volume to go up. So in this case, our temperature went from 309 Kelvin to 367. So we should expect to see a little bit of an increase in the volume for this gas. So our relationship is volume 1 times temperature 2 equals volume 2 times temperature 1. Now this is how this PowerPoint shows the distinction for you, but I want to show you a different way to look at it just because it's going to make a whole lot more sense in the lecture for tomorrow. The way we look at this is actually volume 1 over temperature 1 equals volume 2 over temperature 2. And I prefer to memorize this because you'll see when we put the combined law together, it's going to be easier to remember this, I think. So all they've done, easy algebra, is to cross multiply. So T2 times V1 and T1 times V2. It doesn't make me any difference. Like I said, I'm going to finish this problem showing you this way just because I think it's a little bit easier to look at. So we just plug in what we have. So we have 473 cubic centimeters for volume 1. For temperature 1, we have 309 Kelvin. For volume 2 is one we want to find, and for temperature 2, we have 367 Kelvin. So all you have to do then is to cross multiply and to solve for V2. Like I said, this is just simple algebra manipulation. Don't let it throw you for a loop. And I prefer this this way as opposed to this, even though they're identical. This just helps us a little bit later on. So we go ahead and the math part is the same no matter which way we set it up. So we end up with the volume being 560 cubic centimeters, and it did go up as we anticipated. As the temperature went up, so did the volume. So that's how simple the Charles's law math manipulations are. Just make sure that you have changed your temperature to Kelvin. And sometimes the question may ask you, may give you the volume in cubic centimeters, but ask you what would the answer be in cubic millimeters, the volume be in cubic millimeters. So you'd have to do a conversion here at the end, but just keep an eye out for that, and it should be no big deal to do the problems.